Hi comrades, in this video we're going to look at question 21, and this is about simple molecular compounds and pairs of electrons in molecules that could be described as bonded pairs or lone pairs. In the table below, show the numbers of bonded pairs and lone pairs around the central atom in each molecule. So in the first one we have NCl3. So we've got our nitrogen, which is in group 5. So nitrogen has 5 electrons in its outer shell. With this, it's going to form 3 covalent bonds with Cl. I don't know why I've changed colour. I don't particularly like that, but I've done it now and I'm committed. So we go Cl, Cl, Cl. And we can look in here now. So what we're looking for is number of bonded pairs. Now the central atom is the nitrogen. That's the one that the other 3 are bonded to. So we've got 1 bonded pair, 2 bonded pair, 3 bonded pairs here. So 21A part 1, we'll have 3 bonded pairs and we'll have 1 lone pair. Now silicon Cl4. Silicon is in group, get this right, group 4. Yeah. So just below carbon. So silicon has 4 electrons in its outer shell. Do a bit of hybridization there. And then we'll have chlorines all around it. Very quickly, make sure my diagram's all proper. So 4 covalent bonds with its 4 electrons. So it's just got 1, 2, 3, 4 bonded pairs. There are no lone pairs around the central atom. So we've got 4 and 0. If you were putting 12 in here, it's because you're counting chlorines, lone pairs of electrons, and it just wants the ones on the central atom in each molecule. So BCl3. This is an example you've probably looked at some point for a molecule that doesn't follow the octet rule. So boron has 3 electrons in its outer shell. So it forms 3 covalent bonds with chlorine. So we've got 3 bonded pairs, 1, 2, 3, and 0 lone pairs in boron. And then our Cl2O, they've tried to find an example that isn't water for this one, but it bonds in the same way. We'll have 2 chlorines bonded to oxygen. Oxygen's in group 6, so it has 6 electrons in total. 2 of them are in covalent bonds, 4 are 2 lone pairs of electrons. So our chlorine look like that. And this will have 2 bonded pairs, 1, 2, and 2 lone pairs, 1, 2. So 2 and 2. So that's A part 1. I should have done the shapes at the same time. So NCl3 is going to be, I know this as, if it's got 3 and 1, then it's would look like this. And that is, I call this trigonal pyramidal. But all you needed was that pyramidal part of it. So I'll put that in brackets. SiCl4, a lot like carbon. 4 bonded pairs, no lone pairs. So that's tetrahedral. Then BCl3. Is trigonal planar. And OCl is nonlinear. We used to call this bent, but that's gone out of fashion a bit now, but it still allows you calling it bent. Now the bond angle, if I start with a tetrahedral, when you have 4 bonded and no lone pairs, that gives you a bond angle of 109.5 degrees. Then if you remove one of the bonded pairs and put a lone pair in instead, lone pairs repel more, so it reduces it by 2.5 degrees. So up here, the bond angle will be 107 degrees. In the non-linear, we're now reducing another bond and replacing it with a lone pair. So again, it reduces by 2.5 to get us to 104.5 degrees. And in our trigonal planar, we then have just a straight 120 degrees. If it's planar, then it'll all add up to 360. I suppose not necessarily, because this is in the same plane and doesn't add up to 360. But in trigonal planar, it does. Then it asks us to put a tick by which one's a polar. So that is definitely a polar molecule. It's unsymmetrical. That's symmetrical. That's symmetrical. Unsymmetrical. So that's a tick there. And that is part 2. Then we've got to draw a diagram to show the strongest type of intermolecular bonding between 2 molecules of ammonia. They're specifying strongest because there are 2 types of intermolecular bonding between ammonia molecules. We've got London forces, and we've also got hydrogen bonding. Hydrogen bonding is the strongest. So if we have a look at our ammonia molecule, which I'm not trying to draw in the correct shape, just because it's easier to draw the bonding between them like this, we will have, first of all, a hydrogen bond has to go to from the lone pair on a highly electronegative atom, so that's our nitrogen, to an electron deficient hydrogen. So that's our bonding. We need to show this is an electron deficient hydrogen, so it's delta plus. Our nitrogens will be delta minus, and then each hydrogen is delta plus. And for 2 marks, oh, did it say label the bonding? So it needed you to say that this was a hydrogen bond. And there we go for that. So 1 mark, at least one of the hydrogens has delta plus, and and both nitrogens needed to be delta negative. Then we needed a labelled hydrogen bond between H in one NH3 molecule and lone pair of N in adjacent NH3 molecule. So if you didn't draw it to the lone pair, you lost a mark there. In part C, BCl3 gas reacts with water to form a solution containing 2 acidic products. One of the products, A, has the following percentage composition by mass. Calculate the empirical formula of compound A. So we've got boron, oxygen and hydrogen, and we've got 17.48% of boron. We've got 77.67% of oxygen and 4.85% of hydrogen. So the first step we're going to do is divide each one by its relative atomic mass. So in boron's case, we're going to divide by 10.8. Oxygen, we're going to divide its percentage by 16, and hydrogen by 1. And that will give you 1.62 here, 4.85 here, and 4.85 here. Final step in this one is we're going to divide by the smallest value we've just got here. So that's 1.62. So 1.62 divided by 1.62 is 1, then 3, then 3. So we have boron, O3, H3. And that'll be the empirical formula. Okay, part C, part 2. The molecular form of compound A is the same as the empirical formula. Suggests an equation including state symbols for the reaction between BCl3 and water. So It's telling us we've got BCl3 plus H2O, and that is going to form BO3H3. It's not quite its formula, but we can phrase it like that. The molecular formula is the same of what we just got up there. So that will do for balancing. We're going to suggest a equation here for it. So we've also got to deal with the chlorine. So with the chlorine, we're going to also get HCl formed here. So some of the hydrogen is going to come off and form with the chlorine to form HCl. Just check. No. So that's the first thing we need to do, and now we need to balance it. I know, right. So I was wondering how you knew it was HCl. So just reading back through the question, how do you identify that we've got HCl there? Because one of the other things, it could just be chlorine gas form Cl2. But it tells you at the start of C, BCl3 gas reacts with water to form a solution containing 2 acidic products. So we needed 2 acids. So and this is one of its acids, and this is going to be the other acid. So that's how I knew then this is going to be HCl. So now I just need to balance it. So my chlorines, if I do left-hand side, right-hand side, I've got boron 1, chlorine 3, hydrogen 2, I'll give myself a huge amount of space here, and oxygen 1. And on this side, I've got boron 1, chlorine 1, hydrogen 4, and oxygen 3. So it doesn't really matter which one I start with here to get to balance. I've got no one I want to leave till last. So my borons are fine. Start with our chlorines then. I'm going to put a 3 there to get that chlorine up to 3. And now my hydrogen up to 6. If we go to my hydrogens next, I'm going to need a 3 there to get my hydrogens up to 6 and my oxygens to 3. And luckily then that balances out. And that's 2 marks there for 21. Tricky part with this was spotting that HCl was going to be the other product, and that you needed to spot that it was 2 acidic products, and that's question 21.